Good morning. My name is Colin Gensch, and I've been doing enclosure integrity stuff since I think it goes back to 1984. That's almost 30 years ago. So got a bit of experience, and hopefully I'll be able to impart some of that to you today. So let's back up again to take a quick look at the contents of what we plan on taking a look at today. The survey questions that we had about the venting equations, I noticed that most of you are using the FSSA equations, but we will take a look at the difference between the VdS and the FIA pressure equations as well. The advantage of measuring lower leaks, the ISO method for doing that, multi-fan testing, and then we'll end off with some extended discharge commentary. So moving along, I meant to list a series of articles. Unfortunately, I forgot to do that. We have an article that explains all this in about a 25-page paper that has been oriented for NFPA, and it's been rewritten for ISO as well. It's been printed in 2 magazines so far, not in its entirety, but mostly in the SFPE magazine and also in Firewatch, and maybe even another one. So it is out there, and by all means, if you have not seen that article and would like to see it, let us know. We will attempt to send copies of it out to everyone after the webinar, since we have your email address. So I'll just put a note down here to send the articles. So now we're going to talk about the difference between FSSA and VdS. Where FSSA came from was a research project that was sponsored by and done at FIC, and it happened over about a 4 or 5 year period, starting back, and I don't even want to think how far back it started, but it's been going on for a heck of a long time, and we've eventually gone through the all of the data and come up with some very nice peak pressure equations. So when we're talking about FSSA, we're talking about equations that were derived from experimental data. The VdS and FIA inert agent equations look at peak mass flow rate and assume when you know the mass flow rate that you also know what the peak pressure is. And we'll show you some of the differences later. So in our new software, there's, I'll just drag it onto the screen here momentarily so you can see what I'm talking about. Here we go. Hopefully you can see that. This is the venting calculator for my new software, and it's a whole new section that at one time we had it in a form of a spreadsheet, and we've advanced it remarkably since then, and corrected innumerable things in it, and now have it refined down to a point where it's very, very usable. This is the calculation that you would do prior to designing a system. You can compare agents, you can compare all the different parameters that will affect both the hold time but mostly the peak pressure, so that you can specify the correct vents. Or in the case of NFPA, it is possible to install a system without vents at all, and with a little bit of changes to the design you can accomplish that. This shows you how to do that. So we'll just drag that off the screen for the time being and just take a look at the warning on here. I really don't like huge lumps of text like this on PowerPoint presentations, but since this will be recorded on video, you can go back to our website in about a week and look at this, and or when you run our new software in the next week or so, it'll be about 2 weeks, we come out with the next version. This warning will be on there. So it says that VdS and FIA equations use peak mass flow rates to calculate venting area. we have put defaults into our software so they come up with values that are consistent with the experimental data that we've seen. The peak mass flow rates, or the mass flow rates that your software generates, may give very different values. The reason why we've defaulted these to the values that are those that we've seen in experiments is just so that you won't be fooled into thinking that your peak pressure formulas are correct. And the reason for that is that this is a comparison between three popular peak pressure formulas on the dashed line here, and this was the experimental data that we got. And you'll notice that there's a big gap here, as much as 200 or even 400% error between some of the equations that are used to calculate peak pressure and what we actually got when we did a real discharge. So that's the reason why we put that warning in there. We think that a lot of vents are being installed that are too small, and this would be the reason why. So let's back up again to, this is the warning that we started with here. For inert agents, they have another one for halocarbon agents as well. The FIA equations use exactly the same formula as the FSSA equation, so there at least we have consistency, which is nice. The VdS equations use, again, peak mass flow rates, and as you will see later, they give very, very different results when we are using them to determine peak pressure. The other thing that they do is they only give a positive peak pressure value, and virtually all of the halocarbons give a negative pressure spike, and in many cases the negative pressure spike is larger than the positive. So if you use VdS equations, you will not get a prediction of any negative pressure spike at all, and it's 100% clear that there is a negative pressure spike when a halocarbon is discharged, and to repeat myself, often the negative pressure spike is larger in magnitude than the positive. So we do have that warning on our calculator just so that nobody's fooled. I know that we've had several people that have gotten hold of us and they say, oh gee, how come the VdS equations are specifying such a small vent? And our response is, well, I've not ever seen experimental results that match the ones that they give, so I would tend to favor what I've actually witnessed with my own eyes, which are the FSSA or FIA equations for halocarbon agents. Now, the next one that we have in there is another warning for carbon dioxide. If you look at the NFPA 12 peak pressure equation carefully, it says to use essentially a mass flow rate, but it doesn't tell you what mass flow rate to use, and the assumption would be that you use the average mass flow rate, and that tends to not give the type of peak pressures that we're seeing, and we have again defaulted that mass flow rate to one that we feel is more consistent with our experimental results. That doesn't prevent you from using any mass flow rate that you choose, but we just want to warn people that that's not what we've experienced when we see these discharges live, okay? Now, as far as the software is concerned, getting a copy of it, I can't send you a copy, but you can download it from our website. And if you go to www.retrotec.com, let me just take a quick look here. I'll show you where to find that. Let's see. Pretty easy. Just go to our main page, and right in the front there where it says downloads, you just simply download the enclosure integrity software there, and the current version does not have the peak pressure calculator or the designer calculator in it. There's two ways to calculate it. One is to calculate the enclosure before it's constructed in the design phase, and the other one is to do a peak pressure evaluation after the enclosure is finished. So the new one that appears in the new software is the designer one that you would use prior to the construction of the enclosure. So that's where you would get that. Now, also, if you have questions and you're going through our training, you can also just send those to support@retrotec.com. This webinar is more for general information so that we can get people oriented in the right direction and also get some feedback from you people out there to find out just what it is that you need to know. There's a little bit of a moving target here because conditions are changing a little bit as time goes on. The whole peak pressure field is evolving slightly. Manufacturers are coming out with new agents and new valves and so on, and we're currently adding aerosols on and some new valves for inert agents. And so it's a bit of a changing field, and so we're making sure that our software changes with that. So now we're going to take a look at our peak pressure calculator. I've created a couple of examples here. 8% FM200 into a volume of 95 cubic meters requires 60.1 kilograms. Interestingly enough, 40% argonite into a similar volume requires the same mass of agent. So just an interesting fact that going from helicarbon to inert, we're roughly putting the same amount of mass into the enclosure, although we are putting the mass flow rate into the enclosure for the helicarbon at a faster rate. So since we're discharging in about 10 seconds, we're 6 kilograms per second, and obviously for argonite we're probably discharging in 60 seconds, so we're 1 kilogram per second. So you would anticipate from that that the FM200 would create a much greater peak pressure, but in fact that's not the case because there's a lot of cooling that occurs when that agent is discharged, which tends to offset the mass flow rate. In fact, even though there is a very high mass flow rate at throughout the discharge period, the pressure actually goes down because the air is cooled so much that we get contraction. But let's take a look at what that looks like on our calculator, and just drag that onto the screen here. So the first one that we're going to put on here is FSSA. We're using the NFPA equations, and we're going to put, let's say, argonite in here at 40% discharge for 60 seconds into an 83 cubic meter enclosure, and we hit calculate, and we get 184 square centimeters of PRB that's needed. I'm just checking these to make sure that they make sense. 60-second discharge time. Okay, so let's take a look at the FIA equation, which gives a distinctly higher value here. And that's because it's operating on peak mass flow rate. If we change to the VdS equations, it's roughly about the same. I see what mistake I made here. I'm showing that we're using the enclosure leakage for venting, so I need to get rid of that. So again, FSSA is saying that we need about 1,000 square centimeters of venting. VdS is saying we need around 1,400 square centimeters of venting, and FIA is saying we need around 1,400 square centimeters of venting. So they're all saying about the same thing. If we change the VdS equation to average discharge rate, which is, of course, 1 kilogram per second, we'll notice that the venting requirement drops substantially. So we have to be careful that we're using peak mass flow rate here and not just average mass flow rate. So that would very incredibly underpredict the size of vent that is needed. So that's the first caution that you have to be aware of. And if you're using those equations, it's worthwhile to flip over to the FSSA equations just to see what it says, just to make sure that you got a reasonable result. Again, the FSSA equations are simply based on experimental data, so you know they're pretty solid. Let's jump over to just quickly take a look at, go back to FSSA here and quickly take a look at a different valve, which would be the pro-inert valve. And we'll notice that we're requiring a little bit less than half of the venting for the pro-inert valve. And in fact, if we use the enclosure leakage for venting, here we're saying we're going to use 100% of this leakage, the enclosure leakage will be used as venting. This is the enclosure leakage here. We'll notice that we don't need any vent at all. So this is why this calculator is particularly useful, because it allows you to run through various scenarios and see what is possible. If we were to change this 2.8 meters here up to 3.8 meters, for example, then we would find that because the minimum protected height has been moved up so high that we have to make the enclosure really, really tight. We've got to tighten it up to 142 square centimeters, and that means we need a vent. So this allows you to look at those scenarios and discover those things relatively easily. So let's flip over to FM200, one that everybody's familiar with. We're running around 7.2% here. That's going to require, actually in this case, I think we did our calculation at 8%, so let's put in 8%. And we're going to change the volume to 95 cubic meters. Pretty close, but 95 cubic meters requires 60.1 kilograms, and that says we need a vent on the positive side of 56 square centimeters, and on the negative side 296 square centimeters. So what's different here is that we've defined our humidity range from minimum of 30% to a maximum of 80%, and when we change that, we will mostly change the negative side. So if we allow this to go to drier air, let's say 10%, and we recalculate, we'll notice this goes up. So the degree of negative peak pressure is determined by the minimum humidity. If our minimum humidity is 40%, then we can see that the negative PRV area needed drops. You'll notice here that we require venting in both directions. There now are PRVs out there that will accommodate venting in both directions in the same vent, and this allows you to determine what that venting size is in advance. Okay, so this is our calculation for FSSA. If we take a look at FIA, I think we should have exactly the same values as you see there. If we do a calculation for VdS, you'll notice that it only requires a vent in the positive direction, a much larger vent in the positive direction, and no vent in the negative direction at all, which is where we need most of the venting. Again, we can change our flow rate. Here we're flowing it at a peak rate of 24 kilograms per second. If we were to use the average flow rate, since this is requiring 60 kilograms over 10 seconds, that's 6 kilograms per second. That pulls our peak flow rate down to a value that's kind of similar to what we had before. Again, only on the positive side, and we actually mostly need negative venting, so that's going to cause a little bit of confusion if you use those VdS equations. Okay, so that takes care of the venting calculator for the time being. Okay, so since most of you are NFPA all the way, let's take a look at what we've accomplished in the 2012 version. And I think we've accomplished quite a bit. If we take a look at the old NFPA versus the new NFPA, and we'll take a look at three very common agents, FM200, Novak, and argon, or argonite, are going to be pretty similar in terms of their performance. And we've got two enclosures, various parameters, allowed us to make a comparison. And with the old NFPA, this particular enclosure with a certain leakage would be failing the retention time and also failing the peak pressure evaluation. With the new equations that we're using, we will be passing hold time and also passing the peak pressure evaluation. So you can see that we've got about a 10% improvement here on the hold time side, and about a 50% improvement on the peak pressure side. And I'll show you why that is in a moment. The advantage is even greater when we take a look at the inerts. Here we've got about a 40% increase in hold time, and again about a 40% reduction in the peak pressure. And here's the reason why that is. That occurs when you go from the 2004 version, I believe, to the 2008, which unfortunately is unreadable because it has so many mistakes in it, and to the 2012, which is the first readable version, which is what our software is based on. So let's take a look at why that is. So the reason for that has to do with the relationship between flow, pressure, and area. Now, if we have a hole in a flat plate or a hole that is relatively shallow compared to its diameter, then the airflow through that hole is a square root relationship. So as the pressure quadruples, then the flow doubles. So we take the square root of the pressure, and that tells us basically multiply it by a constant. That tells us what the flow rate is. So this is the square root relationship, and that is an n, or an exponent of 0.5. In a situation like that, a hole that would be measured at 10 pascals or 125 pascals would measure exactly the same hole size, 257 square inches, 257 square inches. In fact, some of the earliest door fans were calibrated with a box with a bunch of holes and flat plates, and they measured the same flow rate regardless of the pressure they were operated at. If we have a different type of hole that would be, say, much longer than it is wide, then it tends to have a different characteristic between flow and pressure, so that when the pressure doubles, the flow doubles. So their area is equal to the flow divided by pressure times some constant. That would be an exponent, or an n value of 1. When we combine a little bit of both, we get an n value that's somewhere between. In this case, I've chosen an n value of 0.71, which is quite typical of a lot of enclosures that we might measure. In that case, the hole size at 10 pascals is 257 square inches. The hole size at 125 pascals is 443 square inches, which gives us a couple of advantages. One, we've decided to evaluate pressure relief vents at 125 pascals. So when we do that evaluation, we see, aha, we have a bigger hole than we thought we had before. And not quite double, but about 60% bigger hole. So that is giving us credit for the fact that that pressure relief vent will actually be, well, it's not so much the pressure relief vent, it's more the enclosure, that enclosure will be leaking more comparatively at 125 pascals than it would be at 10. Now for inerts, the pressure that we're losing agent for inerts is happening at about 1.25 pascals. So there, this 257 square inches becomes like about 150 square inches. So when we use that equation to calculate hold time for inerts, we get a much, much longer hold time. Why? Because the apparent hole, as far as the agent is concerned, is much, much smaller. So the new test procedure that has evolved into NFPA, where we take a test point at 10 and a test point at 50, is able to measure the slope of this curve and take advantage of that fact. The ISO calculations have been using that for well over 10 years, and they've always taken advantage of it. So that's really the reason why. So here we're comparing enclosure leakage for hold time, 257, enclosure leakage for peak pressure, 443. So that's why we're getting the advantage that I showed you before. So now we're going to touch on the advantages of measuring the lower leakage. So as most of you should know by now, if you've gone through level 1 and level 2, our standard assumption is that half the leaks are in the floor, half the leaks are in the ceiling. But that's not typically the case. Here we have two enclosures where we've measured, let's see, what have we measured here? A total of 15 square inches here, and we have a hold time of 12.1 minutes, and this is the total leakage test. Here in yellow, we've done a below ceiling leakage area test where we've measured total square inches of 30, which is again double what this is over here, but we measured a lower leak of 6. So in this case, our retention time is about the same, but look what's happened to the peak pressure. The peak pressures have evaporated, and here the peak pressures were 337 pascals. Here they've reduced to almost nothing. So we've accomplished two things. We've maintained our retention time, but we've eliminated the need for a vent. This is particularly useful in the US, where we are relying on room leakage to a large extent. Now that doesn't mean that we're never going to install PRVs in the US. There are often situations where we must install PRVs, but this would be one way where in measuring the enclosure we can either tell what the PRV size should be more accurately, or do less air sealing in the room, which can save a huge amount of money, or, as I mentioned earlier, have a situation where the same enclosure can pass the retention time or hold time requirement and the peak pressure time requirement without a PRV. But at the current time, we are now required to do a peak pressure analysis to see whether or not the enclosure is in danger when the system is discharged. So we want to find those enclosures that are at risk. Hopefully we can do this analysis before we do the installation and complete it. But at the very least, we should inspect it when it's completed to find out whether a risk exists. Now, the same thing is true with NOVAC. We can again eliminate the need for a PRV, which I'm sure the PRV manufacturers aren't going to be delighted to find out. But what I would like to see is, I would like to see people installing PRVs where they're needed, particularly in the US. And a lot of installations are being completed in the US that need PRVs, and they're not being installed. We really need to get a handle on that one. Same thing is true with inerts, that if we do the below ceiling leakage area test, we may not eliminate the need for a PRV, but we may reduce the size of the PRV that we have to install, so we're installing the right size of PRV. So how do we do this? Well, one way to do it is to measure the total enclosure leakage, which you must do first, and then to measure the below ceiling leakage area test. So let's see what that looks like in the software. So we're going to get rid of the venting calculator here momentarily and drag the software into the screen. And unfortunately, I can't increase the resolution on here at all. So this is new. this is actually a development version where we have the venting calculator, which is on the very first row here. So when we're doing the hold time analysis, we measure the enclosure leakage. In this case, it's an ISO test, so it's doing a multi-point test. Once we've completed that, we can now add the lower leaks test, but we must do the total leakage test first, then we can add the lower leak test. So when we're doing the lower leak test, it's a separate test. We've done the total leak, we do the lower leak test. And how do we do that? Well, you can do the lower leak test by covering the ceiling in plastic, which I've done, I think, 4 times in my life, and takes anywhere from 2 to 6 or 8 hours, depending on the size of the enclosure. Or we can simply use this apparatus here, which I've used hundreds of times, and that can be done in about 20 minutes. And we simply pressurize the space above the ceiling, as we show here in this graphic, with the flex duct, and we measure the lower leak with the lower fan. And the new gauge that we have here is really good at measuring pressure neutralization. So in the past, we had to have 2 people to do this test, where one person was indicating whether the flow across the suspended ceiling was going up or down. Now we can set this up, and we have a set to 0 function on this gauge that allows us to automate this process, so we can set the pressure across the suspended ceiling, if there is one, to 0, and measure the lower leak with this fan. Now in this case, this is the fan that's measuring the lower leak. This fan is not measuring anything. All it's doing is neutralizing the pressure across the suspended ceiling. So here we show the, this was an older version of the venting calculator, where we've changed the value of F, which is a leakage split, from 0.5 to 0.1, and we've eliminated the need for a vent, and we've also allowed the enclosure to be much leakier, which enables us to save a lot of money on air sealing. Even though it takes an hour or 2 to figure out how to do one of these flex duct tests, it's well worth doing. And some of the more experienced testers, I would say that more than half of the tests they do are flex duct tests, because it's the fastest way to pass these enclosures. Now, just touching on ISO momentarily, there's a mistake in ISO that was not in the 2000 version, but is in the 2006 version, and it was almost going into the next version, and I managed to catch it at the last minute, I believe. This value here must be assumed to be 0.15, not 0.5. So this is actually 0.5 in the standard, and it really is a mistake. It should be 0.15. If it's 0.5, the whole section makes no sense whatsoever. So the procedure would be is that you would enter 0.15 as the leakage split. If you pass, then you go ahead and do the next step, which is to actually measure the, well, they call it estimating F. I would rather call it measuring F. So it talks about temporary ceiling upper leaks and da-da-da-da. The lower leakage test that we have essentially measures F for you directly. So for those of you using ISO, the methodology that we described, using either plastic on the ceiling or using the flex duct, works really well to measure the lower leak. Okay, so what I'm going to do is I'm going to walk through a complete test using the software. We've got another 9 minutes or so. And now there will be some features on here that won't be in the versions that you have. I've already stated that the enclosure leakage design section is new, and we're just completing it now. And when you run the software, you go to File, check for updates, and it will automatically go to the internet and update the copy for you. It says my copy is the most recent version. So once you decline to check for updates, it won't do it again until you tell it to. So you won't get those updates unless you ask for them. This is 5.5.24, which is ahead of the release versions that we have out there. So we already looked at the venting calculator. There will be some new changes to settings, which are laid out a little bit more easily for you to use. Here we can change the standard that we use to NFPA, ISO, EN, and so on. The area where we change the peak pressure formulas is unfortunately a different area. So, but we're changing that so that it's a little bit more transparent. The currently called testing parameters. And here we say when we're doing NFPA testing, we use FSSA equations. If we're doing ISO testing, use FSSA equations. We can change that to anything we like. So that will be changing. You will also notice that when you run the venting calculator, and if you happen to choose venting equations for NFPA 12, that automatically turns the agent into CO2. So something to watch for. The venting calculations for NFPA 12 only apply to CO2, so we put that feature in there so that you don't use those venting calculations for any other agents. Okay. So let's just run through the way these sections are lined up is they can all be wrapped up so that you see on these lines here the important details. So here it says in compliance with ISO. So this is an ISO test. If we run down here, we can see that the agent that we've used and the peak pressure, the venting and peak pressure analysis, we can see that we're using FSSA equations. So this is a really nice summary that tells you everything that you've got there, and all you need to do is look at this and you can see everything you need to see. When you want to expand out any one of those sections, you simply expand it out, fill it in, and then you can collapse it back down again so that you can go on and just focus on the area of interest. Here, once you enter your equipment details, they'll stay in there, the serial numbers, calibration dates, and so on. They'll stay in there for successive tests, so that makes it easier. You have the ability to add additional fans here by simply clicking on plus, and we can add 1, 2, 3, 4 fans, and it will add them all up automatically. And if you want to change the models of the fans, it shows you pictures of them, so it makes it quite easy. These are the different gauges that you can use. Currently, none of the testing is automated because the number of points that you have to take are limited. We're looking at automating the ISO tests because in Europe they tend to like automated tests better than we do. If we're doing the NFPA test, it's more trouble than it's worth. So that takes care of the equipment. So here we've got the building section. This will stay constant for this particular group of tests. We've changed the naming of some of these values so that they're more apparent and are more consistent with the standard. In some cases, we've kind of wobbled a bit where we've kind of favored something that's easier to understand, but yet simple. Here, maximum flooded volume, people will always ask the question, if I'm not flooding above the suspended ceiling, do I enter that volume? So I think that flooded volume is the right term to use there. Maximum flooded height again. So we've clarified a lot of that wording in there. We have a pull down here that allows you to do descending interface continuous mixing or extended discharge, which we'll get to in a moment, and all the different agents, both the official name and the, I guess, product name or the manufacturer's name. You can choose either one. And once we get to this section here, we're looking at extinguishing agent information, and we can determine agent quantity by either concentration or mass. You may want to determine it either way. In either case, if you ask for concentration, it shows you the mass. If you ask for mass, it shows you the concentration. There's a couple of things in here that are pretty important. One is that we show the maximum concentration, which is actually the initial concentration, CI initial. We're changing that to initial. This may be more than the design concentration. So in this case, that's the case. The design could be 35%. The maximum or initial concentration could be 40%. There's nothing wrong with that. The minimum concentration is, in both standards, is 85% of the design, not 85% of the initial, but 85% of the design, which is pretty important. And then the specified hold time, which will usually be 10 minutes. If you put nothing in here, by the way, you don't get a result. So let's just close this down and take a look at our hold time analysis. A couple of key things in here. We can either enter Dorfan test values or enter values from another test, which bypasses the data and simply asks you for the leakage area. Fairly straightforward. If you want more detailed results, N value and so on, which most of you have no particular use for, that's hidden. So we've tried to expose to you those values that are most important. Selecting range, over here we actually show you a picture of the range so that it makes it easier to choose the right range, which is one of the big mistakes that people make. We have a second fan in here, you notice. We added a fan here earlier, and let's just put a range in there. There we go. So this is not a real test, but I'm just kind of walking you through the various inputs. So then once we've done that, we do a hold time analysis. We've already clicked on lower leaks earlier, so it's asking us to do another Dorfan test to measure the lower leaks separately. In this case, could be using flex duct or whatever. So once we've done that, we will get a predicted hold time. After we've gone through that, life gets a little bit more complicated because we're now going to be doing the peak pressure, venting and peak pressure analysis. The simplest analysis is that we have no vent at all, and here we say no pressure relief vent. So this is the vent type. And in that case, we're using the enclosure leakage for venting. So that's the first choice. There are other choices in here where we're using gravity vents for both directions. We could be using a gravity vent for positive only or negative only, an electronic vent, an HVAC time delay. What that means is that we may not have a vent in the enclosure, but we may be closing the dampers down on the enclosure. So on a number of installations, what we've done is we've changed the damper closure timing, HVAC damper closure timing, so that we get the added venting that's provided by the ducts that are going into the enclosure already. So it's a great way to get venting, but it does have to be measured. And in this section is where we measure the actual venting of the enclosure. So in this case, we get a positive result. If we have a halocarbon, we get a positive and a negative result. And we'll have a series of warnings and so on that will occur if there are problems and if you're using, say, venting equations that are giving results that might potentially be a little bit wonky. We've increased the number of warnings that we have and given them to you in English statements that will be understandable, hopefully. Let's take a quick look at extended discharge and see what it looks like. I'm going to toss in some values here for enclosure leakage. So the result when you're doing an extended discharge is to determine what the planned extended discharge rate is. And the extended discharge calculation will tell you how much agent you have to discharge into the enclosure to maintain concentration. So the way the formula works is it says what is the agent loss rate, and it will then require that you discharge at that loss rate in order to maintain concentration. I will send you a copy of an extended discharge test report so that you can get an idea of what they look like. They are very common for CO2 protected turbine enclosures, although I noticed that Novak and FM200 is occasionally used for protecting turbines as well. So extended discharge are very, very common for turbine enclosures, and often they'll have an extended discharge for 20 minutes, sometimes even 30 minutes. And it's this extended discharge rate that we're looking for. So this analysis will tell us whether or not this extended discharge rate is sufficient or not. Okay, so I'm going to sign off. Thank you very much for your attention, and bye for now.